Hello everyone, welcome back to this online class. Today we are going to look at how to solve non-homogeneous linear ODEs of the second order. And in particular, we are going to look at the use of inverse differential operators. Now we are given this question. We are asked to solve the following differential equations. In part A, we have d squared y over dx squared minus 3 dy over dx plus 2y is equals to x squared exponential x. Part B, we have d squared y over dx squared minus 2 dy over dx minus 3y is equals to exponential negative 2x times cosine of 3x. So first of all, we need to rewrite those equations in terms of the d operator. So let's define our d operator. You'll say let d be derivative with respect to x, so that simply this implies that where we have d squared, it will be the second derivative with respect to x twice. So now in part A, we write that in terms of d operator, it will be d squared minus 3d plus 2 operating on y to give us x squared times exponential x. So this is non-homogeneous ODE. It has two solutions. The first one is complementary function, and the other solution is the particular integral. So let's start by finding the complementary function. It is denoted by y subscript c as a function of x. Now, how do we obtain the complementary function? What you need to do is to solve the homogeneous part of this equation. Let me call it equation star. Homogeneous part, that's when the right-hand side is equals to 0. So we need to solve d squared minus 3d plus 2, operating on y to give us 0. That's the homogeneous part of equation star. So we need to know what is the auxiliary equation. Auxiliary equation. You simply equate the coefficient of y to 0. So we'll have d squared minus 3d plus 2 is equals to 0. Is it possible to factorize? The best way is to use quadratic formula. Let's see how to find the roots of that equation. Remember, it is quadratic in D. So the roots, when you use quadratic formula, you write d1 and 2 is equals to negative of negative 3. So that is 3, or simply write negative of negative 3 plus or minus the square root of negative 3 squared minus 4 times a is 1, and our c is positive 2. Everything you divide by 2 times a. In this case, our a is 1. So that this can as well be written as 3 plus or minus. Now, here we have negative 3 squared, that is 9, minus 4 times 1 times 2. That's 9 minus 8, which is the square root of 1. Square root of 1 over 2. You see, square root of 1 is 1, so it's like we have 3 plus or minus 1 over 2. So that we can now say that therefore d1, or the first root, is 3 plus 1 over 2, and that is a 4 over 2, which is 2, and the other root, d2, is 3 minus 1 over 2, That's 2 over 2, you get 1. So these roots, they are real numbers and they are distinct. So they are real and distinct. So a case where you have real and distinct roots, how should you write your general solution corresponding to those real distinct roots? So you can say, therefore, y subscript c as a function of x is equals to a constant, let's call it c1, times exponential 2x plus another constant c2 times exponential 1x, or simply x. So this is our complementary function. C1 and C2 are arbitrary constants. That is the first solution of equation star. Let's get the second solution, that is called the particular integral. Now this is denoted by y subscript p as a function of x. How do we solve it? By the method of inverse D operators. So look at equation star. You simply make y the subject in equation star and call it yp to mean the particular integral. When we talk of particular integral, it simply means any particular solution of the given ODE. So when you make y the subject in equation star, this is what you're going to get. So yp is equals to, let me use another color, it will be 1 over d squared minus 3d plus 2, operating on x squared times exponential x. You see here we have a product of exponential function and a polynomial. So this is, I can comment on it. This is a product. What we have here is a product of exponential function and a polynomial. So when you have such kind of a product, what are you supposed to do? What we do is to use the shift operator, or what we call the exponential shift rule. So in this case, we are going to use, you write here, use exponential shift rule. How do we shift it? I'm going to show you how to do that. So we are going to shift this exponential function to the left of the inverse D operator. When you shift to the left, remember in general, when you shift exponential alpha x to the left of the inverse D operator, what you do is to replace. Where there is D, you replace that by D plus alpha. That's how we shift an exponential function to the left of the inverse D operator, so that this can now be written as exponential. Remember, alpha in this case is 1, x exponential x the same as exponential 1x. So that's exponential x. Now, in this case, our alpha is equals to 1. So where you see the d, we are going to replace those by d plus alpha, that's d plus 1. So that our inverse D operator can now be written as 1 over D plus 1, and this is squared, minus 3 times D plus 1, then plus 2. Now, what do we remain with? It is x squared, because already we have shifted the exponential x. So let me simplify the denominator. can work it out somewhere. Let's see what you're going to get. D plus 1 squared, D plus 1 squared minus 3 into D plus 1 plus 2. What is it equal to? This is equal to D squared plus 2D plus 1 minus 3D minus 3 plus 2. And so this is the same as D squared minus D. I can see plus 1 plus 2. That's 3 minus 3. That is 0. So it's just D squared minus D. So what we'll get here is the same as writing exponential x. Then here we have 1 over D squared minus D operating on x squared. X squared is a polynomial of degree 2. So what you do, you could factor out one of the D, because you see this D squared minus D. So you see D is common, so I can factor out D, so that this can as well be written as exponential x times 1 over D into D minus 1. And here we have x squared. How else can you write this? This can be written as exponential x times 1 over D times another 1 over negative 1 plus D operating on x squared. So I'm going to use Maclaurin series to expand this. It must be in the form of 1 over 1 plus or minus D. So I can rewrite that by factoring out negative 1 in the denominator, so that you're going to get this. That you can as well write as it is equals to exponential x times 1 over D times, there's a negative now because I've factored out negative 1. So here we have 1 over 1 minus D. Remember, I've factored out negative 1 here. So that's why we have negative. Then operating on x squared. So when you expand this, let me comment on this one. You write expand in Maclaurin series. Expand in Maclaurin's series. So when you expand that, it can now be written as negative exponential x times 1 over D. Then the expansion for that one is the same as 1 plus D minus D squared. No, not a minus. Everything is a plus. Plus D squared plus D cubed plus so many other terms. This should operate on x squared. So this is now equal to negative exponential x times 1 over D. Now when you take x squared inside, we'll have x squared plus derivative of x squared plus the second derivative of x squared plus the third derivative of x squared plus so many other terms. And so when you differentiate those, whatever we have inside the bracket, we are going to get exponential negative exponential x times 1 over D. Then here now we have x squared plus, when you differentiate x squared, you get 2x plus, when you differentiate x squared twice, you get 2 plus, when you differentiate x squared 3 times, you get 0. And so the higher order terms will also evaluate to 0. Now the question is, what is 1 over d? 1 over d is the same as d inverse. So this can as well be written as negative exponential x d inverse of x squared plus 2x plus 2. D inverse means integral operator. So you can take note that when we have D inverse, it is the integral operator. You're integrating from 0 to x of what we have there with respect to x. It's an integral operator. So I can comment here, integral operator. So when you integrate this one, and don't write the constant of integration. So this negative exponential x, when you integrate x squared, you get x cubed over 3. Then there we'll have, when you integrate 2x, you get x squared, then plus 2x. So that's what we have as the particular integral of that given ODE. So now for you to get the general solution, you simply add those two solutions, the complementary function and the particular integral. So you can just say that general solution is equals to complementary function plus the particular integral. Or you could say y is equals to yc plus yp. Or let me substitute those solutions. Y is equals to c1 exponential. What did we get as our complementary function? Let's check. We got exponential 2x plus c2 exponential x. So that's what I write here. C1 exponential 2x plus C2 exponential x. Then now the particular integral is negative exponential x. Here we have x cubed over 3 plus x squared plus 2x. So this is the general solution of the given ODE in part A, where C1 and C2 are arbitrary constants, which you can determine their values if you're given some initial conditions to apply. But in this case, we don't have the initial conditions, and so we cannot be able to obtain the values of C1 and C2. Let's see how to work out part B. The equation in part B, again, you need to write that in terms of the D operator. Let me take you back to that equation in part B. We are done with part A, so now we are solving part B. Now write this in terms of D operator. It will be D squared minus 2D minus 3 operating on Y to give us exponential negative 2x times cosine of 3x. So let me write it down here and see how again to operate on that using the inverse D operator method. So in terms of the D operator, that equation becomes D squared. The next term is minus 3D plus 2. The whole of this is operating on Y to give us it should be minus 2D. Let me just correct this. This should be minus 2, and the other one is minus 3. So it's a correction. Here we have minus 2D. The other one is minus 3. So that should operate on Y to give us exponential negative 2x times cosine of 3x. So that's what we have in part B in terms of the D operator. So again, this is a homogeneous ODE, which has two solutions. complementary function and the particular integral. So let's get the complementary function, which we denote by y subscript c as a function of x. How do we get it? You need to solve the homogeneous part of that equation, that is d squared minus 2d minus 3 operating on y to give us 0. So you solve the homogeneous part of that equation in part B, so that our auxiliary equation equate the coefficient of y to 0, so that is d squared minus 2d minus 3 is equals to 0. Let's find the roots. Can use quadratic formula. d1 and 2 is equals to negative of negative 2 plus or minus the square root of negative 2 squared minus 4 times a is 1 times c is negative 3. Everything you divide by 2 times a. Our a is 1. If I simplify this further, that will give us 2 plus or minus. Under the square root, we will have negative 2 squared, that is 4. 4 plus 12, that is 16. So the root of 16, everything divided by 2. And so this is the same as 2 plus or minus 4 over 2. So that means again we have two roots. So you can just say that therefore, the first root, d1, is 2 plus 4 over 2. That is 6 over 2, that is 3. The other one, d2, is 2 minus 4 over 2. That's negative 2 over 2, which is negative 1. So those are the two roots. And so these roots are real and distinct. Now, how do we write our solution when the roots are real and distinct? So therefore, the complementary function is equals to a constant c1 times exponential 3x plus another constant c2 times exponential negative 1x, or simply negative x. c1 and c2 are arbitrary constants. Let's find the other solution, particular integral. Particular integral, this is denoted by y subscript p as a function of x. So how do we find it? What you need to do is to make y the subject of the formula in this equation. Let me call it star star. So that you make y the subject of the formula in equation star star. That means you'll divide by the coefficient of y on both sides of that equation to get, let me write it here. You're going to get 1 over d squared minus 2d minus 3 operating on exponential negative 2x times cosine of 3x. The question is, how do you operate on that product? This is a product of exponential function and trigonometric sign. This one is product of exponential function and trigonometric cosine. It should be cosine. When you have such kind of a product, what are you supposed to do? We are going to use the exponential shift rule. What does it mean? That we need to shift this exponential function, exponential negative 2x, to the left of the inverse d operator. How do we shift it? We replace where there is D, we replace D by D plus alpha. In this case, our alpha is -2. So D plus alpha is D plus -2, which is just -2. Remember, it is D plus alpha. In this case, our alpha is -2. So when you take D plus alpha, you get D minus 2. So that's what you're going to do. So therefore, this can now be written as exponential -2x 1 over D minus 2 squared minus 2 times D minus 2 minus 3. Now we remain with the cosine of 3x. So let's open the bracket in the denominator so that we see what you're going to get. We can do it here. You write this D minus 2 squared minus 2 into D minus 2 minus 3. That should give us D squared minus 4D plus 4 minus 2D plus 4 minus 3. And so this is the same as D squared minus 6D plus 8 minus 3, that is plus 5. So that's what we have when we open or simply expand the denominator. So let me rewrite this equation now with the new result that you have found. So this can now be written as exponential -2x 1 over D squared minus 6D plus 5 operating on cosine of 3x. Now we are back to case 2, where you operate on trigonometric cosine. What are you supposed to do in this case? You identify your new alpha. Our new alpha here is, remember, cos alpha x. Alpha is equals to 3. So we are going to replace D squared by negative of alpha squared. That's what you're supposed to do when you operate on cosine or sine. That is case 2. You can refer to the PDF notes. So where we have D squared, we are going to put negative of alpha squared. So in this case here, our alpha is equals to 3. So this means that alpha squared is equals to 3 squared, which is 9. And so it means negative of alpha squared is equals to -9. So therefore, where we have D squared, we are going to replace that by -9. So that this can now be written as exponential -2x 1 over -9 minus 6D plus 5 operating on cosine of 3x. We still have a D operator in the denominator. We need to get rid of all those D operators in the denominator. So this can as well be written as exponential -2x. Here we have 1 over negative 6D minus 4 cosine of 3x. And you can factor out negative so that you have negative exponential 2x. Of course, that's -2x. And here we have 1 over 6D plus 4. And then that should operate on cosine of 3x. You see, I cannot replace d, but we only replace d squared. So I need a way to introduce another d squared in the denominator so that I can replace that by -9. So what do? We multiply the numerator and the denominator by the conjugate of the denominator, so that this can now be written as exponential negative, this negative of exponential negative 2x. When you multiply by the conjugate, we'll have 6d minus 4 over 6d plus 4 times 6d minus 4, operating on cosine of 3x. And so I can multiply the denominator. So what will it give us? Let's see. Negative exponential of negative 2x, 6d minus 4 over, denominator we have difference of 2 squares, so we'll have 36 d squared minus 16, operating on cosine of 3x. Again, we need to replace the d squared, so you put where we have d squared, you replace that by -9, so that this can be written as negative exponential negative 2x 6d minus 4 over 36 times -9 minus 16 cosine of 3x. Now work out the denominator. What is 36 times -9 then minus 16? You can press that in your calculator. That should give us -340. So that this can be written as negative exponential negative 2x 6d minus 4 over -340, operating on cosine of 3x. And now you see the -340 will cancel with the other negative, so that we have +340. So this can as well be written as, or 1 over 340 exponential negative 2x. Then we have 6d minus 4. These are now d operator operating on cosine of 3x. And I told you, when you have the d operators in the numerator, they simply mean that you are differentiating. And when they appear in the denominator, it means you are integrating. You need to take note of that. So if I open this bracket, this is the same as writing 1 over 340 exponential negative 2x 6 times derivative of cos 3x, then minus 4 cos 3x. When you differentiate cos 3x, you get -3 sine 3x. Derivative of cos is negative sine. So this will now give us 1 over 340 exponential negative 2x times, now that will give us 6 times -3 sine 3x, that's negative 18 sine 3x minus 4 cos 3x. And I can simplify this to get -1 over 170. Of course, I factor out, let me factor out 4. No, I factor out 2, so that I have that. Here we have exponential negative 2x. Here we now have 9 sine 3x plus 2 cos 3x. So this is our particular integral. To get the general solution, you need to add those two solutions. So you can write here that general solution is simply the complementary function plus the particular integral. Or y is equals to yc plus yp. Let me replace those solutions. You can say here, or y is equals to, what did we get as our complementary function? It was c1 exponential 3x plus c2 exponential negative x, now minus 1 over 170 exponential negative 2x times 9 sine 3x plus 2 cosine of 3x. So that is our general solution. C1 and C2 are arbitrary constants. So I can bracket this and say this is our general solution. So in those two examples, I have illustrated how to use the exponential shift rule when solving non-homogeneous ODEs of the second order. Thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving the inverse D operators method. Bye-bye.